Hi everyone, and welcome to our first OpenML Tools demo day, where we will demonstrate everything that we have. Hello, and welcome to our first OpenML Tools demo day, where we will demonstrate everything we have developed so far for oil and gas, released it to public, led several workshops, and will cover everything and explain you how to use it, how to download, and how to sign up for courses. And everything we do is free, available online. Please type your questions to the Telegram chat or anywhere on YouTube broadcast, so you'll be able to receive feedback from our team. My name is Anna Dbovic. I'm really happy that you joined us today. Please forgive us for a little delay, and we'll be happy to lead you on forward. So we are a little bit behind the schedule, but I'll try to keep myself super fast and lead to the other guys. So today we'll talk about SEISMIC Pro, the processing library, SEISMIC QB, interpretation, and we'll also cover partial differential equations solver with neural networks, as well as batch flow, our core library that we have developed so far and still supporting. Everything we have published is available on GitHub. We support open source, and we hope that you'll join us in this journey. So we started in 2019 with the support of EAG, and this is our major partner, and I'm really happy that EAG members are joining us today. Thank you guys for supporting us. First, we started in the Middle East. We led a hackathon in Bahrain, releasing real data sets, non-synthetic data, because we keep in mind the idea that only real data sets can support and move forward the industry of oil and gas and machine learning in production. If you are still trying to do your work on synthetic data sets, you might reconsider, because this is not giving you as great results as could be done on the real data sets. Hopefully, this year we'll launch several more hackathons, releasing new data sets with the support of our new partners who has joined us in NVIDIA and as well as EAG annual conference. And basically, the idea behind our work is that oil is not as simple to extract, locate, and drill anymore as it has been before. So old software, proprietary tools are not supporting the needs. It should be transferred to machine learning and neural networks, because those are the core algorithms that can perform well in the uncertain situations that we are facing right now. And basically, exploration is the main field for oil and gas implementation of machine learning, simply because it has the most value of the error. If you keep the error in the upstream, it leads to greater losses on the next steps. And if you implement machine learning in the later steps, it means that you probably have missed your billions potential by now. So if you are still avoiding exploration and machine learning implementation exploration, you should reconsider, because this is the main field of interest. The tools that we'll be talking right now are covered in the schedule, so this is the links, and we'll provide them in the video as well. And we basically keep four main ideas behind our work. First, and most important, we do everything speeding up. We do everything in high precision on real data, and we do it with the quality control metrics, which we will totally explain you today. And those are not some imaginary numbers that no one supports. It's created with the support of geoscientists who know how to actually validate results of machine learning algorithms. And this is key feature of our work, and I really hope you will enjoy it. And any questions, please forward to Telegram chat. My name is Anna Dbovic, and I'll be transferring to SEISMIC processing to Anton in a second. See you soon.
Hello, my name is Anton, and I'm going to talk about seismic exploration. And during my speech, you will know what the problems geologists face during seismic processing, and how the machine learning helps to solve these tasks. Seismic surveying is the first stage of oil and gas exploration. During this stage, the data that represents the geology of the region of the interest is obtained. This data is used to construct a geological model that allows making accurate predictions about the region of interest. In order to make precise geological models, the raw data needs to be denoised, clean, and structured. And this is the main purpose of the seismic processing stage. It consists a lot of iterative tasks performed manually by experts, which is time-consuming. Moreover, mistakes in the processing stage make seismic interpolation extremely difficult. It leads to wrong estimate of oil deposits and their location, which is a result of huge loss. Machine learning is key not to speed up seismic processing, but also allows you to obtain predictions comparable to an ensemble of experts, not relying on single specialist opinion. On the slide, you can see the major step of seismic processing pipeline. Green marks stages that we already covered with our tools and models, while the red stages are the ones who we are not attended yet. All solutions are based on our framework named SEISMIC Pro. It's basically open tool written in Python. You can find it on GitHub also. And it's designed to enable easy and convenient performing of usual processing routines and training of neural networks for seismic processing tasks. Our framework provides tools to lead, process, and visualize pre-stacked data in different representations from raw traces to semblances. This allows one to apply various processing procedures and employ different approaches to train neural networks for a wide range of tasks. And today, we're going to talk about some of these tasks. First task, it's a geometry correction. The problem appears when the actual locations of the receivers and sources doesn't match the planned one. This might happen due to the human factors or some technical issues. Unaccounted for displacements in the survey geometry introduce errors into all processing stages, from noise to staking. Now, to correct geometry, experts manually evaluate tens of thousands of gathers, which takes them up to a week, because usually the error with the receiver or the sources are very late. Therefore, specialists need to remain attentive because it's really easy to miss an error. We have developed a network that allows us to automate the search of these errors, and in few hours, it allows to reduce the number of seismograms that needs to be checked by 97%. Our model determines if there are any geometry errors in whole survey. The main idea is that the near offsets first arrival wave field of a shot gather should be perfectly flattened after applying linear move-out correction. If a shot or receiver position is incorrect, then the wave field will be continually broken. For example, on the slide, on the bottom right image, you can see the really broken image. It seems like something wrong with position of source or the receiver. We develop a model and train it for 5 different surveys, and it trained so well, so it can confidently detect the displacements up to 30 meters. And the model is really fast, and it's able to process up to 100 gathers per second. Now let's have a look at the model works, how the model works for real data. In this example, the survey contains 33,000 of surveys, and the model classified 900 seismograms as a possibly containing geometry errors, which left experts with 35 times less data to process and validate. A traditional procedure carried out independently proved that the model have found all misplacement sources in the survey. The map shown on the slide represents the model's predictions. Green areas indicate that there are no geometry errors, while the red areas indicate that there are suspicious seismograms inside that needs to be checked. In addition, you can see 3 examples of seismograms. On the top, you can see, on the top and the middle, you can see the good one example, and one with incorrect source position on the bottom. Second, a survey contains 52,000 gathers, and our model classified 2,500 as seismograms that possibly contain the errors, which left experts with 20 times less work. As before, we can find examples of a good and bad seismogram on the slide. Next task we are talking about is first break picking. The task can be formulated as follows. Given a seismic trace, determine the arrival time of the wave traveling from the source to the receiver. These times are later used for studying near-surface velocities and subsequently performing static corrections. Existing semi-automatic picking tools tend to make mistakes on traces with a lot of noise before the first break, so the stage remains time and labor intensive. Since the experts need to adjust parameters for different areas of the survey and manually examine the results, it takes days or even weeks to process large segways. The neural network solves the task in just a few hours and surpasses the auto-picking tool by accuracy. To ensure the quality of predicted first arrivals, the expert checks the results, manually chooses the examples from the huge survey, and this approach requires also really a lot of time, and experts should be attended on the task. And this approach did not cover all seismograms, so probably he was wrong, but experts wouldn't know about it. We have developed a new approach for quality control by constructing a visual map. Basically, you can see an example on the slide of a field that allows us to assess the quality of predicted first arrivals over the entire area. The red dots on the slide, on the map, represent the areas with high variability in near-surface signal velocities. Most of these points indicate errors in model predictions, although some of them may indicate areas with unusual subsurface. And now we will see an example of how we solve this problem using our library named SEISMIC Pro, as I told before. All our libraries are written in Python and open source. You can find them in the description or in translation or in Facebook or in Telegram, sorry. Also, we use a library named Batchflow to create and train our models. I'll use Jupyter Notebook. It's a very convenient and interactive software that allows to run a code and show the result in place. And we train the first break picking model on the data from the 3 surveys conducted with seismic vibrator sources. In the second cell, we load the seismic gather from the SIGY file, and in the next cell, we will plot the data to get familiar with it and labels. Top image shows the whole seismic gather and the bottom one zooms into the first 50 traces from it. The red dots on the plot correspond to the first break picking times. Note that the distinct amount of the noise in the trace before the first break. This is a typical artifact from vibrator sources, and it makes first break picking as a real hard task. Now let's take a look at the model. The task of first break picking we solve as a semantic segmentation where every sample of the trace is being classified as signal or non-signal one. Here, with a few lines of code, we define our model architecture with 1D convolutions and important training parameters such as optimizer and learning rate. 1D means that we predict the first breaks for each trace independently. In the next cell, you can see the training pipeline. This pipeline allows us to easily train model. The model is trained for 1,500 iterations with batch size a little bit more than 1,000 traces, and the whole pipeline takes about 22 minutes to converge on a single GPU. In the next cell, we just save a model, and now let's go to inference. Here you can see the inference pipeline. It's a little bit longer than the training one because we just want to save the result and show them to you. But the other lines are pretty much the same as for training. Testing pipeline process 15 gathers with over 5,000 traces in a few minutes. It takes more time due to the extra processing actions required for visualizations. And you can see on the resulted picture, you can see a lot of outliers, and the mean absolute error in the end, it's pretty huge, and it's almost 20 milliseconds, which is really bad. The model often reacts on the noise that precedes the first breaks, and it seems that it lacks some prior information about neighborhood traces. So to fix this issue, we decided to apply 2D post-processing after our model using another neural network. And now we are going to the next notebook. Here we use the same data as in previous, but now the inputs of the model are the stacked predictions, and the labels are the stacked masks from the previous notebook. Validation is carrying out on the same partially labeled survey from ongoing project. Let's load the batch of the data and take a look on it. The first picture shows a SEISMIC gather. The second one shows the stacked predictions of 1D model, and the last one stacked of ground truth mask. Here you can see the outliers in predicted masks that we want to remove. We use the same model as previous, but now it's 2D convolutions. Training pipeline a bit more complex, but still very compact. This model train a little bit less, only for 1,000 iteration, and take about 10 minutes to converge. In the next cell, we save our model and define config to load it in future. Inference pipeline is pretty the same to training one, but a little bit longer because we also want to load the data and visualize it. This whole pipeline takes 5 seconds to process 15 gathers, and now let's take a look on the result obtained after neural network post-processing. The blue points are predictions of the 1D model. The green one are predictions of 2D post-processing model. You can see that it removed a great number of outliers. The mean absolute error is also dropped. Probably you can find the result not very awkward, but in a few minutes we will compare the result of this model with auto-picking tool, and you'll see that it's really good results. Nevertheless, it's not the limit of these models. We are conducting experiments to improve 1D model and remove the remaining outliers after 2D post-processing. Okay, let's return to slides and let's discuss the result of first break picking model on the real data. Here you can see the field contains 33 million of traces. The model predicted the limits of the first signal in a few hours. We construct a map to measure model quality, and as we can see, it's all green, so we did a great job. And examples of good seismograms are shown on the slide on the top. Red zones on the map and those with high signal velocity variability are partially caused by the external causes. In this case, it happens because a large number of traces was the zero traces, which means that only the zero amplitude was in these traces. It occur to broken receivers or some human problem and should be removed before the first break picking, so it's not the problem in this case. We also compare a neural network with auto-picking tool that is tuned manually. And it's easy to see that the neural network picking show a higher accuracy over almost the entire survey area because neural network map covers with blue, it's best result, and after picker map covers with green, that is also good but not great. Another point of view on the result is histograms that show the distribution of difference between the picking first arrival time and the one calculated from the constructed topography model. It can be seen from them that the average picking error made by a neural network is less than by auto-picking. The next slide shows the model advantages, such as a higher correlation of well data and speed of training. Also, if you are interested in this task, you can find more about first break picking problem on our Medium page. See there and read, it's really awesome article. Next task we are going to talk about is ground roll attenuation. This is a noise that causes seismograms. This type of noise is generated by near-surface waves that have a low velocity and low frequency, but significant amplitudes. It overlaps reflected waves and masks the signal of interest. Ground roll attenuation is a basic step of seismic data processing, and its quality strongly affects on user steps. So it's really important to do it really well. This noise experts suppressed in a semi-automatic mode. They select filter parameters using just a few seismograms from the field and then apply the parameters they found to the whole survey. These suboptimal parameters may be chosen for a particular gather, resulting in poor noise attenuation because some gathers are have a really hard structure, and some parameters may lead to the bad results for them. We have created a neural network that filters the ground roll automatically. Let's have a look on the example of the model. Our approach is that we first define the area of the seismogram where ground roll is located. Here in the middle you can see noise part of the signal, and its name ground roll mask. And then we try to reconstruct the noisy signal in that area only. Such approach allows to changing the signal only where it's needed and leaves the signal without noise unchanged. Let's have a look on example with real data. And there are 3 images on the slide from left to right. The first image is a raw gather with a ground roll. Middle image shows the result after neural network processing, and the last image is the result of semi-automatic processing. We figure out that the result of our model and semi-automatic tool are completely coincide. So, the most disadvantage of semi-automatic approach is that it takes, first of all, it takes days to achieve the good quality, and first of all, it's like took a lot of time because the expert iteratively try other parameters and see how it looks in the result, and calculation of one parameters took a day or more. So the overall process can take weeks or even more. While our approach works automatically and takes only hours to achieve the same quality or the same amount of data. If you are wondering about the model more and want to know how we control the quality of this model, welcome to our Medium. We have a detailed description about it there. Okay. Next task is the stacking velocity. Here we also have a look how we can find the stacking velocity and build a pre-stacked cube with our library. Let's go to the notebook and have a look. To apply kinematic corrections and build post-stack cube, it's necessary to define a stacking velocity for whole field. And experts group several common midpoint gathers located nearby to obtain a supergather. Using the found supergather, the expert calculates the vertical velocity semblance and manually picks the velocity values. The manual process took a lot of time. Therefore, supergathers are built with a step of 1 or 2 kilometers, and the velocity between is interpolated. This leads to a huge information loss and also affects the quality of further stack. The notebook is constructed as previous first break picking notebooks. Here we also, in the first cell, we also define a survey we will be working with and other important parameters. Also, we generate a supergathers with small step in order to reduce information loss. On the output of the cell, you can see the indexes of created supergathers. High amplitudes near first break negatively affect semblance as well as stacking velocity, which will be calculated on its basis. In order to reduce this effect, we set all area above the first breaks to 0. This procedure called gather muting, and the muted area is defined by offsets and corresponding time velocities. Also, we define some hyperparameters for velocity model, such as start and end velocity, and other important parameters. Now let's have a look on one step of whole pipeline that finds stacking velocity for a single supergather. On the first image, you can see the raw supergather. Second one show you a muted supergather. You can notice that the upper part is muted and doesn't contain any amplitudes. Next image shows you a vertical velocity semblance with found stacking velocity. Large amplitude of the semblance indicates that the selected wave velocity describes the hodograph at the given time really well. So the found stacking velocity generally should pass through local semblance maximas. The red color corresponds to the higher spectrum value, and in our case the velocity looks really well because it passes almost through all red areas. The calculated stacking velocity in further used to perform a normal mode correction of the supergather. All hadograph on the resulted image are expected to be straight. As you can see, they look straight. In the next section, you can find a pipeline that automates the calculation of stacking velocity. It does not require expert attention, therefore it can be applied to each beam of the field, which leads to a better detailing in post-stack cube. Moreover, supergathers are prepared and preprocessed in parallel. This allows us to calculate described stacking velocity just in a few seconds. Moreover, supergathers are prepared. Next, we use the found velocity to create a post-stack cube. In the last cell, one can see the slice of the post-stack cube that has been built based on a stacking velocity. The pictures show clear lines of the horizons at all times. This allows us to conclude that the stacking velocity was found correctly. To sum up, we can say that the developed pipeline allows calculating the stacking velocity at each point of the field and stacking the amplitude of a cube for a survey contained some million of traces in just a few minutes. Okay, now we will describe last but not least task today is a deconvolution. This procedure surpasses multiple fractions of and improves the temporal resolution of a signal. Its parameters are selected on a small sample of data and are applied to the entire survey. But areas with atypical geology where the selected parameters led to unsatisfactory results may be skipped during the quality control because it's really selective. Appearing at later stages of processing and interpolation, they will require to return to deconvolution and start from the scratch. We have developed a convenient tool that allows you to calculate the properties of a signal and build the visual map that reflects the quality of deconvolution over the entire survey area. Having found a problem area in the map, an expert can visualize the signal attributes on a seismic cube in just a few seconds, in order to better understand the reasons of deviation in processing results. One can find the examples of these slices on the left, or on the right, of the slide. Also, we apply the algorithm on a real survey with 6 different parameters of deconvolution. Using our visualization approach, we are able to compare the results and find the best one. As a result of this work, the processing opinion, which shows the most significant and uniform improvement in the signal properties on our quality maps, was also accepted by the expert for future work. To conclude, we have described now the machine learning approaches that help experts to process pre-stack gathers and make sure that our approaches really work for real surveys. And also we got acquainted with the library for seismic processing named SEISMIC Pro. Of course, today we have not covered all the tasks we are engaged in. Just stay tuned for the news. We will let you know where we will talk about our another tasks in future. Just subscribe everywhere. And now you can ask your question in chat and I will answer them in a few minutes. And for now it's all, and I will just give a word to Sergey that will tell you about seismic interpretation task. Thank you.
Hello, my name is Sergey and I'm here to talk about seismic interpretation in DEET. After the processing stage, we are left with a three-dimensional seismic volume, which accurately reflects underground formations. The goal of seismic interpretation is to outline key structures and locate potential oil reservoirs. Ideally, we want to describe oil saturation and potential profitability of the entire field. To compute such a model, we need to find both vertical and horizontal structural boundaries, as well as to detect facies of multiple kinds, for example, alluvial fans and fluvial channels. I will start with the horizon detection task, as it is the easiest to grasp and showcase all the important concepts: dataset and task definition, metrics, model architecture and training procedure, and finally using the model to predict on the entire field. Then we will turn to other tasks and show how to apply similar ideas to solve them as well. Seismic horizon is a boundary between two layers of rock. It is easy to see them on any type of seismic data, even for a non-specialist. They are used to outline potential oil reservoirs and provide essential information about the field. Naturally, during the exploration stage, seismic experts track a lot of horizons for every region, and any inaccuracy at this point leads to huge profit losses due to underestimating or overestimating the amount of oil. Despite the importance of precise horizon detection, for the past 30 years, surface tracking in oil and gas has hardly changed. In most companies, one or more geological experts manually label every point of the target horizon, with some aid from autocorrelation software. Programs extend the label from a point to its neighboring traces, yet they work only where the reflection is distinctly visible, the level of noise is low, and the geology itself is trivial. In complex seismic cube areas, which are the most interesting for us, specialists still resort to hand labeling, spending up to half a year on each of the fields. Despite the seeming simplicity of the task, there are a ton of potential mistakes. Over the last year, we've gathered a dataset of more than 50 fields with hundreds of horizons on them, and with the help of our metrics, of which I will talk exclusively later, we were able to identify a huge amount of inaccuracies. Obviously, most of them are not as severe as those shown on the slide, but nevertheless, even tiny deviations from the tracked phase here and there substantially alter the resulting structural model of a field. The reason for all of these mistakes is definitely not the lack of qualification of geologists. It is the process itself. When a human must manually inspect and label an enormous area with little to no help from his tools, he is definitely prone to errors. We propose to completely change the horizon detection process with three goals in mind. First of all, we should have an automatic method of evaluating the quality of the tracked surface. That would significantly reduce the time spent by geologists, as they would need to inspect only the areas where the horizon is already deemed unreliable. Second, the process of creating a structural model should be transparent and clear at all stages, with estimates of time to finish all necessary horizons and faults. And finally, we want to speed up the process, the detection steps, so our models should be fully automatic and fast. The new workflow of horizon detection consists of following steps. First of all, we compute the map of geological complexity of a field. We do so by comparing distribution of traces along horizons. Then we compute the grid for carcass labeling. It is tighter in hard areas and very sparse everywhere else. Then a human tracks the horizon carcass, no more than 20 slices of data total. It is used to guide the model which exactly surface to track, and we evaluate the quality of this labeling, so geologists can fix any mistakes right away. After that, we train a neural network on a provided labeling and apply it to create a surface that covers the vast majority of the field. Then we use two separate neural networks as a post-processing step. One of them stitches even the smallest holes, while the other aims for more accurate phase tracking. And finally, we assess the quality of the resulting surface. This gives a way for the express interpretation of the horizon. Also, if we see unsatisfying results, we can throw more computational resources on complex places. This entire procedure takes less than 3 hours for each of the horizons, and we can run multiple parallel processes to speed it up. so it takes the same 3 hours or even less for any amount of surfaces to track. From the machine learning point of view, the task is a binary segmentation, so the main architecture we use is an encoder-decoder. We extensively researched all of its parameters by looking over building blocks and their configuration, pyramid modules, loss functions, visual attention, and other hyperparameters of training process, such as the shape of crops and augmentations to use. It is worth noting that the task is closer to edge detection than to segmentation, so we also apply some tricks from that field, like the dense composition of blocks. We keep an eye on emerging architectures. Unfortunately, some of the newest additions, like segmentation transformers, require a lot of data to train and are not applicable in our tasks. When we apply the model on crops, we see that it easily tracks horizons even in places with complex geology. For example, it is able to correctly detect surfaces in places of faults and velocity anomalies. To get the prediction for a field, we stitch together predictions from individual crops. This is highly optimized and parallelized procedure with tons of implementation details, resulting in a high-fidelity surface. To assess its quality, as with the quality of any other horizon, be it handmade or model-generated, we developed multiple metric maps. We compare amplitude distribution of the data along horizon both in a local and global manner, resulting in a top view map, where anomalies are highlighted with red color. Some of them are actually geological complexity like faults and noises, but we can filter them later. Overall, this map can be used even by not an expert for making conclusions about how good the tracking is. We have tested our technology on more than 50 archive fields with known horizons, and the conclusion is very simple. Had our workflow been available 5 to 10 years ago, horizons would be produced months faster and with better quality at the same time. For the last year, we have been applying our workflow to all fields we can reach, totaling in 16 projects. As our horizon detection technique is way faster than the usual interpretation process, specialists can outline more of the promising locations, resulting in a better understanding of underlying geology. The QR code leads to a detailed report and comparison between human and machine learning interpretation. Here are a few slides from it, where we showcase our technique on different fields and horizons. We can clearly see that model-produced horizon is of the same or better quality. For more details, check our horizon report, which will be posted in our Telegram channel. The proposed procedure requires some attention from humans, mainly to label carcasses. The next logical step is to detect some of the horizons with no supervision at all, and we have already implemented a few methods of doing exactly that. They are able to locate 50 to 100 horizons on an average seismic cube, and for more subtle surfaces we can always fall back to carcass interpolation algorithm. Seismic interpretation is definitely not only about horizon detection. We have just demonstrated how to apply machine learning to surface tracking, and we can take the same blueprint and use it for other crucial steps of the geological workflow. One of the more similar entities to the horizons are faults. They are vertical discontinuities, which can be seen by either visible shifts of texture in the seismic image or amplitude anomalies. Faults come in multiple kinds, yet all of them are very similar to horizontal reflectors from a machine learning point of view. All we need is a data set with labels, and the same binary segmentation machinery can be used to a great effect. Unfortunately, we need separate labeling for each type of the faults, and also we want to use one pre-trained model on new fields with no additional labeling from experts. This calls for a better quality of training datasets and normalization techniques, but overall the machine learning method is very similar for horizon detection task. We train model on small subvolumes, then use model for predict on the new field, and stitch small crops together into the whole cube. Unlike the previous task, we need to apply more post-processing to faults. One of the algorithms is used to thin out produced labels, while the second extracts point clouds and fault sticks. We are actively developing them to work even in the most complicated scenarios. In the end, we get three-dimensional folds, which we can overlay with horizons. Together, they form all necessary components to create a structural model. Another model of ours is capable of locating fluvial channels along labeled horizons. From a technical point of view, once again, it is very similar to the fold detection. We use a pre-trained model to find objects on new data. Here we can see the hand-labeled channels in the middle and model prediction on the right. Clearly, neural network is capable of labeling the same channels as well as a lot of other potential structures. On another field, where there are no human labels, we can see that model successfully detected lace-like objects, which were later confirmed by our geologists to be channels. Note that the task of facies detection is not as computationally demanding as horizon or fold detection, so it takes literally minutes to complete. All of the described algorithms are contained in our SEISMIC-QB library, which is a collection of tools for fast interpretation of post-stack seismic data. It can work with dozen labels in different formats, generate data from seismic volume according to a probability distribution, evaluate quality of underlying structures, and apply mathematical, machine learning, and geological augmentations to data. Along with the benefits listed on the previous slide, we created a new format for storing post-stack data. We reduced the amount of disk usage by utilizing three-dimensional structure of underlying seismic cubes, as well as optionally applying quantization to amplitude values, increasing the loading speeds at the same time by a factor of 50. Our format is not as universal as SegY, but it reduces the memory footprint by up to 5 times, which is very convenient when working with terabytes of data. Our SEISMIC-QB framework is based on batchflow, which is another library developed by our team. One of the next presenters will tell you more about its capabilities, but the main features are configuring the most complex models with simple dictionaries, generating data in multiple parallel threads or processes, and also clear and easy to read pipelines. Here we can see the timings for our models on the same field. We can see that even the slowest of them can be run overnight, and importantly, all of them can be run in parallel. So when a new seismic cube arrives, we just run all of them on multiple GPUs and collect the results in a matter of hours. We always look not only for software but also hardware improvements. Fortunately, we live in times when new accelerators are produced quite often, and by using the latest GPUs we can speed up our models up to 3 times compared to the timings on the previous slide. So that concludes my talk about current state of our tools for seismic interpretation with machine learning. In the nearest future, we will move towards an end-to-end model of seismic interpretation, as well as create an interface to allow every seismic specialist to run our models on a local station by simply pressing the button. If you have any questions, please don't hesitate to post them on our Telegram channel, and I will gladly answer them.
Hello guys, now we're going to be talking about PyDance, a recently developed framework for solving differential equations with neural networks. So, as you probably understand, modeling oil and gas, the dynamics of oil and gas fields is an important task of oil and gas fields exploration. Good model of a field can help to get an estimation of oil and gas debits depending on the choice of location for wells, thus greatly reducing risks and increasing economic efficiency of any project. Unsurprisingly, the industry of scientific computing has already produced a set of good solutions for the task at hand. Basically, all of these solutions are highly optimized numerical solvers of partial differential equations governing the motion of oil, gas, in porous media. Recent developments of deep learning allow to use neural networks for solving systems of differential equations. Yet, there has been a lack of convenient framework for research and further experimentation. In an attempt to fill the gap, our team has produced PyDance, an open-source Python framework for solving partial differential equations using neural networks. Hopefully, by the end of this presentation, you'll have some idea how to use PyDance, how to solve a differential equation of your choosing. So, first of all, we're going to discuss why bother solving differential equations with neural networks at all. Then we will briefly discuss mathematics behind PyDance and similar algorithms. After that, we're going to demonstrate how to solve a simple partial differential equation or PDE problem with PyDance. Lastly, we will be talking about new setups of partial differential equations related problems that become possible with PyDance and neural networks. These are parametric equations and equations with adjustable coefficients. So, why use neural networks at all? True, direct modeling with fully known inputs is already highly optimized in current numerical solvers. However, classical numerical solvers are hardly susceptible to parallelization. That is, the difference in performance between GPU-based machines and CPU-based machines is only twofold for classical numerical solvers. However, the same difference for neural networks-based algorithms can reach thousands and even tens of thousands. In other words, it stands to reason to solve differential equations with neural networks to achieve greater parallelization and efficiency of computation. And PyDance is a Python framework that allows to do just that, solve partial differential equations with neural networks. Among other important features of PyDance, first of all, it allows to handle tasks with more interesting setups, such as parametric families of equations, and equations with trainable coefficients. Now, we'll briefly discuss mathematics behind PyDance. As it happens, PyDance is actually based on a simple mathematical algorithm called deep Galerkin. Quick recall, in the original Galerkin algorithm, we attempt to approximate the solution to a PDE problem with a linear combination of basis functions. We only need to find those coefficients that yield the minimum, the optimal value of residue between the left-hand side of the equation and the right-hand side of the equation. On the contrary, in deep Galerkin algorithm, we approximate the solution to a PDE problem with a neural network rather than a combination of basis functions. Yet, in a similar manner, we minimize the residue between the right-hand side of the equation and the left-hand side of the equation. However, here we optimize the weights of a neural network. Now, closer to examples. In order to solve an equation in PyDance, we have to make some preparations. First of all, we need to explain to PyDance what is the equation that we want to solve. It can be easily done via simple language of tokens. As you can probably see on the screen, generally speaking, one writes down an equation in PyDance in the very same way he would do it on paper, using token D for differentiation and tokens like sine, cosine, plus, minus for common mathematical operations. The second thing that we need to do is to define the neural network architecture that will approximate the solution to the PDE problem at hand. Importantly, PyDance allows to set up a large family of neural network architectures in a couple lines of code. For instance, the configuration dictionary on the screen defines a fully connected network with 3 hidden layers and tangential activations. Adding or removing letter F to the layout allows to add or remove a hidden fully connected layer to the network. Last but not least, we need to set up a sampler of points from the domain of the equation. The thing is, each PyDance model is trained iteratively, and on each iteration the training procedure attempts to make the equation as true as possible on this specific batch of points. In the example on the screen, we want to sample points from either uniform distribution or normal distribution. The latter component can be used to make an approximation better in a specific region of interest, for example, corresponding to the location of a well on oil and gas field. Okay, at this point we only need to combine the defined parts into one dictionary, wrap the whole thing up in a model instance, and press the feed button for running the training procedure. And in a second we will obtain the solution approximation to the PDE problem at hand. So, you may probably wonder, now we know how to solve partial differential equations using neural networks with PyDance. But again, common numerical solvers are already quite efficient when performing this task. So why bother using PyDance and neural networks in here at all? Well, the thing is, a lot of value lies in modeling systems with uncertain and unknown inputs. Speaking of oil and gas, these uncertainties can reside in media properties, including the spatial distribution of porosity and permeability of a field. Naturally, this uncertainty can be handled by running thousands or hundreds of thousands of simulations, each one for a specific set of values of unknown parameters. Yet, this can take days of time. On the contrary, neural networks are naturally adapted to incorporating uncertainty. It turns out that introducing variability and uncertainty in, say, spatial distribution of porosity of oil and gas field is as simple as adding another input to a neural network and training it to solve the perturbed equation. Consider the equation on the screen. On the surface, it looks like a simple first-order differential equation. However, a parameter epsilon makes it a parametric family of equations rather than a simple differential equation. Setting up PyDance to solve this family of equations comes down to adding a token P, that stands for parametric, to the equation. In the example on the screen, token P wraps up a letter E in the configuration. This gives PyDance an indication that E is not a variable, but actually a parameter. And the equation that we need to solve is actually a parametric family of equations. True, training such model takes more time than running one simulation of a classical numerical solver. However, there is still a tremendous win in performance when compared with running thousands of simulations. And of course, we need to do just that to handle the uncertainty in input parameters when using the classical approach. Alternatively, consider the following equation. In this case, we also have imperfect information about the equation in the form of unknown coefficients alpha and beta. However, to compensate for the missing information in the equation, we have some additional constraints on the solution in the specific points in the domain of the equation. When tackling this setup, commonly referred to as inverse problem, PyDance will try to not only solve the equation at hand, but also determine the unknown coefficients, and thus fill in the gaps in missing information. In doing so, it will rely on additional constraints given in the setup. So, in the presentation, we've discussed the new emerging area of research, solving differential equations using neural networks. We've also gained some understanding how this domain of research can bring more efficiency to fields of oil and gas modeling and computation of numerical solutions to partial differential equations. We have also seen how newly developed Python framework PyDance can be used for experimenting with solving plain vanilla partial differential equations, as well as more interesting partial differential equations setups. These are equations with uncertainty in inputs and adjustable coefficients. Gladly to start experimenting with solving PyDance differential equations with neural networks, you only have to install PyDance via pip or git. So that's it for today with PyDance. Presenter will give you some idea about the core framework that we use for our research, batch flow.
Hello everyone, I'm Svetlana and I'm very happy to be speaking with you today. As you can see, I'll tell you about batch flow. Batch flow is an open source Python framework to handle data, train machine learning models, and do all related things. You can use the library to construct very clear and expressive pipelines that describe data loading and processing, model training, validating of the model, inference, matrix computation, and so on. The framework also includes a variety of methods for image processing and ready-to-use architectures of neural networks in TensorFlow and PyTorch. Moreover, batch flow has a convenient interface for running parallel experiments on multiple GPUs. Here you can see the whole process of loading and processing batches and training the model. It can be described as a pipeline that you can easily read and change. The entire functionality of batch flow is aimed to describe complex ML procedures as pipelines. There are many similar frameworks. Take a look at the short comparison. We focus on applied libraries, and there are several reasons to use batch flow as the core of all of them. Batch flow allows you to store almost all data processing and model methods in a single pipeline, rather than to split it up into separate parts implemented using different libraries. It contains a flexible instrument to configure ML models. All projects have the same structure, so it's very easy to start a new project and join a team as a new user or developer. Our framework has a well-organized hierarchy of classes. To understand how bash flow works, you need to understand its main classes, and now we will briefly discuss all of them using examples. More detailed description you can find in the documentation. Often you deal with huge datasets and batches have to be created on the fly from the storage. For example, satellite images can take tens of gigabytes. With the files index class, you can create a unique index for each data item, consisting of path to images. That class contains necessary methods to generate batches of indices to take items from a dataset. You can use an index in the more complicated and more probable case, when each item consists of an image and a mask stored in one folder. To make an index from a folder, just add the DIRS flag into a files index object creation. If a dataset can be stored in memory as an array, for example list, each item can be specified by a numerical index. The dataset index class makes it possible to work with them in a similar way. It's not enough to load batches to train a model. They must be processed in some way. The batch class contains transformations to be applied to batches. To define specific methods for your data that can be changed into a pipeline, add a method with the action decorator. You also can use the images batch class and predefined methods to load, process, and augment images. The pipeline is a way to change batches and standard actions. For example, let's describe a pipeline that loads and augments batches. All actions defined in the pipeline are lazy and will be executed when the run method will be called. There are also ways to sample different parameters for each batch item. You can split a pipeline into logical parts and after that sum them. As we said previously, a pipeline describes computations lazily. To execute all of them, call the run method. The bitwise left shift joins a dataset to the pipeline. A dataset object represents a collection of elements and knows how to create batches, use an index and process them with a batch inherited class. It's also a lazy structure and in general doesn't store any data, only information about it. Don't worry, batch flow includes a predefined, not pre-trained model zoo written in TensorFlow and PyTorch. It's enough to import and train the most used architectures, for example ResNet, DenseNet, UNet, EfficientNet, and many others. The example on the slide shows how to use the unit class. A model initialization and training actions in a pipeline can be defined in the following way. In the simplest case, a model config includes only hyperparameters to configure a network's output, but it also can include many other things. For instance, you can even define an entire architecture with just a model config. Among other things, you can speed up training by using various tricks that batch flow provides. For example, you can split a batch into parts, compute and accumulate gradients, and thus train a model on large batches. Such a procedure can allow for faster convergence. You also can speedify training by computing gradients on multiple GPUs. Batch flow also includes a research module which allows to easily evaluate multiple parallel experiments with different configurations. It includes instruments to describe complex domains of parameters to generate their configurations, create a flexible experiment plan as a sequence of callables, generators, and batch flow pipelines, parallelize experiments by processes and GPUs, save and load results of experiments in a unified form. You got to know the main ideas and structures of the library, but it is only the tip of the iceberg. With batch flow, you also can speed up training process in several ways by multiple GPU utilization, prefetch batches, perform multiple parallel experiments with ML models, use monitoring tools to check resources utilization, easily construct complex sampling schemes. Our main focus is the development of applied libraries SEISMIC-QB, SEISMIC Pro, and PetraFlow for geological implementations, radio, cardio for medical applications, and others. Batch flow serves as a common base and contains functionality common to all tasks. Thank you very much for your attention. We hope you will enjoy using our framework in your future projects. And now we will have a few minutes for answering the questions and discussions. Thank you.
It has been a pleasure seeing you online, getting your questions, getting direct messages, getting feedback in Telegram channel and both on YouTube. So now we have to accumulate all of this and post it. Everyone who has registered for the event will receive the link to the recordings, the materials that we have used, and some more benefits of being, part of the event so far. Please provide us any feedback that you consider important, because this is the first event of this sort, but there will be more. We'll launch online courses with EEG, we'll launch webinars, hackathon, and many more in the upcoming year. I'll also include the calendar of events for the next year that our team will be present. Thank you for being with us, for your time and effort, and hope to see you on our next event further on. See you soon. Bye-bye.